Yes, sir. Yes, please go ahead.
So before this, we have just this is not this. So still we are talking about drought management, but we are just talking and talking. So starting with this first, we will see the case study of each and everything. So you get a good idea about how we can use the GIS and remote sensing. So first case study we have start with how we can easily utilize the GIS and remote sensing in groundwater potential mapping. So as you have, this is a published paper in ISPR journal. It's, I don't know the exact factor, but it is a good peer-reviewed journal. So we have recently published this paper. So in these things, what we do is for Jalgaon area, Jalgaon it is a uh, area in Pune, sorry, it's Maharashtra. It is district Jalgaon for whole Jalgaon district. I am working for postdoctoral fellows. At that time, we have done this study, and recent some we do the study with the help of trace data. So for this Jalgaon area, what we do is we identify where there will be a good groundwater potential is present. So for this area, you get all the information. You can read these things code here. So how much is the Jalgaon district? North, it is in North Maharashtra, semi-arid climate. So rainfall will be uh, less and other things so high. So that things we will identify based on these maps, because for this area, whenever you have to identify any groundwater potential or any decision making maps, you require many maps as we have discussed. So this is the first map that we are using. Sorry, that we are using is this ground a rainfall map. So we collected the rainfall of that area using TRMM, that is thematic rainfall mapping mission. So all the you can easily see that the distribution of rainfall in the area you can easily demarcate. So this demarcation of or visualization of rainfall is very easy whenever you use any GIS or remote sensing based images. So you can easily interpret that this red area is having a lowest rainfall, while this area or these packets or these patches will be or these grids are having higher rainfall. So all these things you can easily map. So this is one of the basic layer that required for groundwater potential mapping, because the main factor that influence the groundwater potential will be the rainfall. Why? Because if there will not be any rain, so groundwater flux or groundwater recharge could not happen. So this is one of the basic or major influencing layer that we have to consider. Next will be your the soil type. So soil type in that area is alluvium soil and some sandy soils are present. So all these soil types are we can map. So the next, then there will be a land use. So all these influential layer we are used with the help in the GIS background. So as I previously said that whenever you have to do a spatial data integration, so this all this spatial data, so rainfall, then geology, land use, land cover, then your drainage, then your soil type, uh, then there will be a lineament density, geology, then this will be a crest data, and this will be a weather zone data. So all this data and its integration will be done in the GIS background. So for this we are using the methodological framework, like we are using the GIS crest data. This crest data we are used for uh, used to identify groundwater storage anomaly. So how much groundwater storage anomalies are present, or how much is the groundwater storage. So the storage we will identify by using the GRACE data. Then we integrate all these hydrological layers such as rainfall, soil, slope, dynamic integrate. in the GIS background, we have given the AHP MCDA weightages. So many of you know this AHP is analytical hierarchy process. So this is one of the basic method that we generally use for giving the weightages to the layers and the subclasses. So all these layers, these are called as a layer or thematic layers. This thematic layer is having a subclasses. If you see in the legend, this legend is having a subclasses. So there will be a high rainfall, moderate rainfall, low rainfall. So all these subclasses will be given the layer or the information. So, so these layers will be given the weightages. So all these weightages and thematic layer are given weightages based on the data. So all this data and images are classified or given the weightages based on the ASP methods, and finally we generate the recharge potential zone map of this area. So so
Sir,
this
can
will
you
be, you
show
can
that flow chart on the right hand side top which you had prepared? Can you zoom it and show?
this one.
Yeah, yeah.
Can you see that?
Yeah, yeah. Okay, so methodology you have explained in that.
Yeah, methodology I am explaining. So methodology is we are using the satellite data, conventional GIS data, and climate data also. So in methodology, we are using DEM, digital elevation model. So based on that, the Sentinel data and Landsat data we use to identify the lineament in that area. Based on the DEM, we can identify the drainage, also topo sheets, the geospatial data. Then we use the radiometric calibration to identify the land cover of that area. So based on that, we also get a conventional data like a geology, soil depth, and then climate data such as rainfall. Then we do the reclassification of this data. We classify all this data into five classes. So if you see your year slope, rainfall, land use, land cover. So all this data we reclassify. All these data we are reclassify into because why we reclassify data, because we have to combine all this data. We first reclassify into a pixel size of 30-meter resolution or more than that, whatever will be the resolution applicable. So in 30-meter resolution, then we do the geospatial weightages with the help of this AHP method. And then we also use the FR, that is frequency ratio model also. So to identify weightages and ranking to the given to that classes. So or layers, ranking will be given to the layers and weightages will be the given to the classes. So that we will do, and then by overlay analysis we will identify groundwater recharge as well as potential zones. So all these things we will do, and then we will do the validation and model analysis. So this model analysis we have done, and we identify this will be the recharge potential zones of that area. This will be the result. So this is already a published paper. So here you can see that the changes in the recharge potential and the main influential factors that are affecting this area. This it can be easily identified with the help of methods such as GIS and remote sensing, because there is always a what you call as a spatial variability in the area, and the synoptic view of any district you can easily do with the help of GIS and remote sensing. So as we said that the recharge potential will be higher in the Tapi alluvium area, where the valley fields and high lineament and density zones are present. So why there will be a more recharge? Because all the lineament is nothing but a linear structure who allow the water to percolate into the groundwater. So for that area, the density will be higher, and the potential of recharge will be more, and groundwater potential will be also more. And in the alluvium area, as it is near to the river, so water potential will be more. So moderate potential in the pediment part, and then the lower potential will be in the basaltic plateau where there will be a steeper slope and more infiltration. So this analysis you can do in the GIS background. Then there will be a grace-based groundwater trend analysis. So we have done also the groundwater trend, how the trends in that area. So this groundwater trend of starting with 1991 to 2019, how the groundwater levels get depleted or the recharge rate get changed, and this will be gives you that there will be always a decline of groundwater storage anomaly ranges with 1.2 to 2.5 meter in the area. So you can easily map, like there will be always a groundwater depletion in that area, and there will be a seasonal depletion during pre-monsoon. As we always know that whenever the March and April will come, all the groundwater levels will goes down, and then there will be how the recovery will be happen. So there will be a partial recovery and insufficient offset of obstruction is there. So we can easily give this some how the implication of that area. So artificial recharge structure shows the local resilience, and the gray cell means all these are the conclusion of that study. So how we can demonstrate. The next study will be uh, how you can for this will be interannular annular variability, where you can identify how there will be a changes in the rainfall pattern as well as groundwater level depletion. So this data will give you the strong seasonal oscillation in gray signals. So for these areas, Rajasthan and other places, they have do the analysis, and they found that the interannular variability or the changes in the groundwater or water resource is strongly linked with the monsoon, and there will be a persistent decline of the recharge despite of the monsoon. Because why this happens is nothing but due to the over exploitation of water resource in that area. And also this type is happen mainly in the semi-arid basaltic region, like Jaga also. So these are the results that are compared. The next thing is that, as I previously said, we have uses the different data sets. So how data set for Maharashtra, as I said that there are different data set there uses. This is the first data set that we for presently we are working is a GRACE TRMM data, that is thematic rainfall mapping mission data. So you get a rainfall per years, and the lowest rainfall will be in this part and higher rainfall will be the. So this per year, the rainfall will be higher in the western Ghats, while the other part of Maharashtra will be somewhere this part is the rain shadow zone. Then there will be a lowest rainfall also. So this all this synoptic view for rainfall you get from a rainfall TRMM data. Next will be the slope. So if you want to identify the slope of any area, you can easily do with the help of GIS and remote sensing. So this will be the slope map for our area or Maharashtra. Then there will be a aspect, that is how the slope will be changed in the direction. Then we do this analysis of topographical wetness index. This will be one of the major indices that we use to identify groundwater storage anomaly of our area, because it uses soil, slope, and uh, layers and the DM layers to identify how much is the wetness index, and this lastly will be the geomorphology. So all this data we are using. Uh, we are using to identify the groundwater storage anomaly of Maharashtra area. With this, we are also uses the GRACE satellite data, as I said, because the GRACE data. Sorry. For the GRACE data, we are using layers such as soil moisture, evaporation, and the canopy water content, and we finally get this is higher. Means this is coarser resolution data, so we get how much will be the changes in the groundwater storage, and this groundwater storage will be measured as there will be uh, uh, the storage or TWS, that is total water storage, will be the groundwater plus soil moisture plus canopy water plus surface water will be gives the total water storage minus the grace water. So you will get how much will be the storage anomaly in that area. Next will be the analysis of using this GIS remote sensing in water resource is identification of site suitability potential for soil and water conservation measures. So this is also one of our published papers. So here also we are similarly using the dam derived parameters like slope, relief ratio, drainage density, bifurcation. So if you want to see the detailed methodology, you can see like here we are using the Aster DM soil topo sheet, then water resource map. So based on this, we prepared a slope map, drainage density, geology, and other things. You can prepare a geomorphometric analysis like linear, aerial, and other aspects, and then we give a weightage sum, and finally do a overlay analysis with the for soil, land use, and settlement map to identify suitable site potential for soil and water conservation measures. So, and we do the ground truthing analysis. So this will be your site suitability map. So what are which areas are suitable for? So it is the where there will be a higher slope, there will be a lower potential or lower these things, and based on this we do the watershed prioritization. Which watershed will be prioritized very high, very low, and other things. So all these things, site suitability mapping for and this suitability mapping we are do mainly for the check dam, percolation tank, contour trenches, and we have classified this into suitability classes of very high, moderate, and low. So this is one of the case study of what we do for water resource management. Then next will be we and this is one of our also published paper in elsewhere or not Springer. So where we have identified the groundwater polyphoric zone for groundwater recharge also, and groundwater extraction also. To identify these prolific zones, we are using various layers and simple layers such as rainfall, slope, and geology, geomorphology, and lineament. Here we use the different method of weighted overlay analysis. So if you see over there, rasterization and weighted assessment of each features we have done, and then we do the groundwater potential or polyphoric zone. And for here, we are using the multi-influencing factor. So which factor are affect more or influence more on other factor? Such methodologies we can easily integrate in the GIS. So lineament will be more influenced than the drainage. So such a way that lithology will be more influenced by the drainage. Land is land cover will be uh, more influence the lithology. Then land is land cover also more influence the slope. So based on this multi-influencing factor, and we do the groundwater overlay analysis to identify the weighted overlay analysis for area. Sorry. Um, so the groundwater weighted overlay analysis of the area, and we try to identify the potential. So we validate the data with the post and pre-monsoon wells, and the fluctuation of 57 wells. You can see over here this. The wells are seen over here in blue colors that we use to validate the data, and we identify where there will be a good zones from where you can extract the water, good to moderate, and moderate to low. So the high yielding wells are strongly correlated with lineament density and gentle slope. So all this analysis we can do in the water resource management with the help of GIS and remote sensing. So here also we can do the recharge potential zone maps for groundwater storage. So this is also similar methodologies where we identify the recharge structures, and these are the groundwater yield storage and groundwater recharge zones also. So to identify the groundwater potential. Also we can identify the recharge impact also. So uh, uh, these are some case studies of key observation, whenever there will be irrigation canals that are flows through the area, there will be always a resultant will be uh, resultant will be the higher will be the recharge in that area. So this can be also observed with the help of rise in the groundwater level. So all these mappings are we are done, or the studies has been done, that rise in the water level, that is post monsoon water level, shows the measurable recovery of uh, changes near the check dams and percolation tanks, especially in fractured zones. So the fractured zones, because we are working in the Jala Swaraj 2 project also, where we identify that whenever there will be a highest recharge, the rise in the groundwater levels, that is flooding of water levels, there a groundwater level where then there will be a good water to the these things, borewell also. Then there will be a improved in the sustainability. The dugwell and borewell recharge, if we increases, there will be a good reduction of air, good water availability during summer also. Then there will be a reduction in seasonal depletion and enhance the climate resilience. Because if we increases the water, it will reduces your climate things. So this is also studied with the help of GIS and remote sensing. Then there will be a next of we can also identify the hydrological. This is one of our research output, or the new methodology we have developed to identify the hydrological response of watershed using the prioritization. So here we this, if you see over here, this is already a published paper, Springer thing. So it is already a published paper things that we have taken. This is our my PhD topic published paper. So here we used, or here we are develop a hydrological response based methodology. That is a new methodology developed in my PhD things. So here we are using the different methods such as frequency ratio, fuzzy logic, and analytical hierarchy in the GIS environment. So what we do is, I just explain you the methodology. Here we are using the total number of pixel and groundwater occurrence pixel in frequency ratio method, where we have uses the DGSLR compound index that we have developed to identify how much is the hydrological response for each watershed prioritization. For that, we have taken the layers such as drainage density, geology, slope, landforms, landfall and rainfall for my study area. Sorry. So all these layers we integrate in the GIS environment using the frequency ratio, fuzzy logic standardization, and analytical hierarchy process to develop a new indices of DGSLR and generate a hydrological response unit for our study area. So this hydrological response unit will be we have developed for our area, and it is already published in a paper having a more than 5 factor. So this it is classified into various zones of, as I said, the GIS is used in watershed prioritization. So watershed is nothing but a water resource where this you see that all this part is called as a watershed, because all this watershed, the river, that is Shivganga river, that is flowing from this area, and all the waters will drain from this area. So this all this part is called as a watershed. So this watershed we divided into sub watershed, and these sub watersheds we have divided all this part all the basin into 8 watershed, and 8 watershed we sorry, 8 sub watershed. So all these sub watershed we prioritize with the help of our DG SLR newly developed indices. So based on this, these are the results, and we found out that it will be showing a good resilience, or good correlation with, sorry, good correlation with the output that we are getting of whether where there will be a priority or not. So as you see that this part is having a higher what you call as a priority because it is having a elongated shape, and all the runoff of this area will be easily flown down. And this if this is part, this red part, if you see over here, so it is having also required a higher priority because it is in hilly terrain. So more soil water conservation or more water conservation measures and groundwater recharge structure should be given in that area. So, like this hydrological response based prioritization, we can easily do with the help of GIS and remote sensing studies. This is some of the informations that we are collected, or uh, we are done with them, or it is collected from the net also. So, if you see over here, uh, I don't know how much you can see, but some part if you see the precipitation is increases, the groundwater policy changes. So in this area, if you in this area of Indian subcontinent, so Indian subcontinent groundwater depletion and precipitation is decreases. So in this area groundwater is depletion and precipitation is also get decreases. So all this information about a synoptic view you can easily get for the Indian subcontinent. So here also you can see the groundwater depletion is happen. So similar studies has been happen with the help of GS and remote sensing. So this is some of the what you call as a case studies that we capture that gives the regional groundwater storage beyond the monitoring wells. Because whenever you want to analyze major areas, for that GIS and remote sensing gives you the synoptic view. It will detect the long-term depletion and delay in recovery of climate variability, and the complaints such as GIS and MCDA will use the water prioritization models. It will also helps to identify climate stress and basis target recharge intervention. So all this help in the policy level decision making. So how you can easily do the sustainable management of water resources. As I previously said that that groundwater quality issues of any areas you can easily study. So for this, for my study area, we have identified the health risk using the GIS and remote sensing. Because the groundwater quality in that area, we have done the analysis of pre and post monsoon water level parameters, and we identify the pollution index, groundwater pollution index for that area. We identify that 18% of the samples are above during low to moderate, and post monsoon there will be a dilution due to rainfall. And but which samples are polluted? 18% samples are polluted, but which samples are polluted? So for that, we go for contaminant analysis like boron, chloride, and which exceeded the WHO limits. So we map that data over here. So you can identify like climate-based observation that if these red areas, adjust to, so there will be a more total hardness, okay, and there will be a hard means very hard water is present in that area, and there will be a what you call as a hard water, and but moderately hard water you can't see anything anywhere. So all these things easily mapping will be done by interpolation in the GIS background. So the total hardness you can see, also the PIG, that is pollution of groundwater pollution index, where you can see that there will just the smaller pockets of low pollution, and the other areas is significantly polluted during the pre as well as in the post monsoon season. So all this mapping like uh, so this mapping will be do for water resource management with the help of GIS. The result interpret like there will be pre-monsoon because of the evapotranspiration and reduced recharge and longer groundwater residence. The pre-monsoon season or these pre-monsoon maps will be showing a higher pollution while there will be a semi-arid climate and higher inter-annular variability of rainfall replenishment. The post-monsoon season, after the monsoon happens, there will be a lower pollution. So, but as the area is having a hard rock aquifer, there will be a low buffering capacity against the climate stress. So, like this, we are already. This is also one of our published paper. You can see over here there is a springer that directly we have taken a capture of screenshot. So we identify the carcinogenic health risk for the area that is resident public in that area. So carcinogenic risk we will identify with the help of hazard health index. So this hazard health index we try to identify THI, total hazard index for adult, then for children, and then for infants. So total hazard, how this varies. This is for post monsoon. This is for pre monsoon. So you can see that no health risk, but no health risk will be higher in this area in pre-monsoon. So the results show that the children will be the most vulnerable, followed by the adults and infants. So if you calculate the health risk for the children, you can see that this map, both maps are for children. Here you can see that no health risk layers, that is blue color lines, are blue color patches are very less as compared to red colors. So you can easily say that the fluoride contamination or the children are more vulnerable as compared to adult and infant. The pre-monsoon season also shows that the health risk concentration will be higher. So this pre-monsoon season also show that due to the groundwater get contaminated and there will be a higher residence time of groundwater, there will be a higher health risk for the human beings. And the major contaminant for these are the fluoride, boron, and nitrate is also identified. And also the results show that the hard rock is limited to the dilution and evaporation and low recharge will under the climate stress will be the more culprit for the groundwater or the health risk of this area. So, what is the adaptation is this supply of risk-based water supply and the treatment before the water to be used before get consumption into the water by the water purifier or softener that should be provided in that area. So these are the basic some case studies that we have done. So after this, we will start with our next thing, that is urban water management. So in urban water management, we will do with the water net or piping mapping. So all the net, so the piping management we have to identify from where the one pipe or the water is distributed in this area. So the distribution and demand will be always defined based on the how much is the demand. The distribution will be more in that area. So this will do. Then there will be a flood prone area, because as we see in Pune also, um, the more river based residency or river, what you call as a river side residencies are increases in day by day. This will result into the flooding, encroachment of the human into the flooding areas. So if you try to identify that areas where there will be more flooding, that it can be easily identified and the flood risk of that area will be nullified. Then there will be irrigation management like soil moisture, as I previously showed you the soil moisture layers. So soil moisture layers can be easily identified like micro remote sensing, and the moisture wherever this is not happen in this practice is not going in India, but wherever there is US where they have a more farmlands of thousand of hectares of farmlands are there. So they will take real-time images and they will identify where there will be a low soil moisture. So they will irrigate that area firstly. Then there will be identification of crop health. This is also recently they are done with India or in specifically in Maharashtra, where they do the crop Bima Yojana, something like that. So they have to identify the health of a crop. So they will just go and identify the health of a crop or nutrient with the help of satellite images. What they do is they take a freely available images from Landsat and they try to identify the health with the help of NDVI. So NDVI shows the health of a crop. So they will allow or they will pass the crop bima or they will reject that based on their analysis. Then efficient irrigation planning also, as I previously said, it can be easily do with the help of soil brightness index, NDVI, soil or modified soil water indexing. So this indexing will you try to identify where there will be irrigation is required. So that irrigation water will be given to the places where there will be water is required, and the other part we will do water saving practices. So in water saving practices also, where which part is required, a deep irrigation, micro irrigation practices. So which if we given a water to the higher slope area, there will be always more overland or rainfall runoff relationship will be more. So this rainfall runoff relationship we can identify, and we save the water in that area. Also, we have discussed that wetland monitoring and conservation. So, starting with wetland, because we have not done this study, we don't have a case study for this, but we know that the wetland will be an area where there is always a water. So, these are mainly the areas near to the seashore. So, that areas we can detect with the help of GIS and remote sensing. And this wetland cover monitoring also we can regularly do to identify monitor the area. Then the if you develop this wetland, the health assessment like a chlorophyll content, then soil moistures and other things we can easily do with the help of GIS and remote sensing. Then the biodiversity conservation, how the diversity and wildlife is present in that area, and how we can go for wildlife conservation. This biodiversity conservation is done for this Sundarban Delta, that is also a wetland area. So for that area also, good wetland conservation plans are prepared with the help of GIS and remote sensing. So all this analysis we can do with the help of GIS and remote sensing. Next will be the coastline water monitoring and mapping. As we have said, or as we have seen that on the water quality monitoring we can do with the help of satellite data like chlorophyll content, then salinity and pollution tracking also. Salinity is nothing but there are two types of salinity: inland and seaborne salinity. So inland salinity, there will be a more hardness that previously said, and waterborne or seashore salinity will be the higher amount of salt water intrusion in that area. That will also easily map with the help of GIS and remote sensing. Then fishery management, as we have discussed, if there will be a more chlorophyll content in that area, there will be a more fish catch. So that chlorophyll content can be easily monitored, and India is also using the same technique to go for fishery management in Indian peninsula regions. There are also snow and glacier monitoring. So in water resource management, we can go for snow and snow cover with the help of their cloud condition. So how there is a snow cover management also. Snow, how much snow is the present, and we can map the area and we can measure its thickness also based on the gravity based analysis like grace and other things. Then there will be a glaciers extent. So, so how the glaciers will melt and the rate of melt of glaciers, because the glaciers can melt and the white portion of snow get reduced. So based on the density also grace and other things, micro lidar and radar data also we can get to know how much is the glacier extent is present, and based on that we try to identify or interpolate the melting rate. Then the snow flow and impact of water flows, um, like a river, the precipitation pattern, terrain information, and river networks. We try to identify the seasonal snow flow and its water flow in the main. These studies we have mainly done in the Lidar Valley of Himalayas, where we have tried to identify the seasonal flows, because snow melt in the region and it flows through the channel. So how flows will happen, and we get the water of not a seasonal, perennial water flows in that area. So that can be easily identified, and based on that, if we get information about how we can use the water flow for ensuring adequate water for drinking, irrigation, and hydropower project in that area. Also, there are some challenges of water resource management. We have seen all this data, but the thing is that the data that we get is do not have a good resolution, because all this data we get from a different resolutions. So, a simple example I will give the resolution. Now, here you can see that the resolution of this data is 110 kilometer by 110 kilometer. So one pixel is having a 110 kilometer by 110 kilometer area. While in this area, this pixel data is having a resolution of 5 kilometer. Sorry, 2.5, 10 kilometers. Sorry. And in this area, it is having a spatial resolution of 25 kilometers. So there is always a challenge whenever you study for a bigger areas or any smaller areas. The spatial resolution is not similar, and whatever data we getting is not a radiometric corrected data. So whenever you do a what you call as a GIS based study, this problem every time comes that the data resolution and accuracy will be always create a problem, because the pixel size of one data is 110 kilometer and the same area is having a 5 kilometer by 5 kilometer pixel. How you can correlate result of both the data? Because for 110 kilometer you having a one value, and for other map it is having a 5 kilometer by 5 kilometer, you have a more than 50 values. So the resolution will be different, and the final output will be always different. So these problems comes, and for that we are go for data what you call as a interpolation or downscaling of the data. And downscaling we mainly do with random forest, MLR, and then AI and other methods. But that methods always create errors, and that accuracy will always get hampered. So that is a major challenges whenever we do GIS remote sensing analysis. Next will be the data sharing and integration, because in US all the data is available on USGS website, United States Geological Survey, or any groundwater related survey. All the data for each and every parcel of the US is always present. But for India, it is very difficult, or it is not possible for getting a data for Indian subcontinent. For Varis, we have data, but the resolution of Varis will be the highest, means coarser resolution, not a final resolution. So that data integration and data sharing is always problem, because NREC will don't give you data. They charge a good amount of money to give you data, but the sharing of data will be very less. Then next will be the cost and accessibility. As I said, the data they will charge, and they charge like anything. Means for US you get the data free of cost. That is for the Indian subcontinent also US is producing data or giving the data like a Landsat data. But for Indian they don't give data. They give a data of these three, or before resource set 2, and the resolution is 56 meter or 30 meter resolution, while the Landsat is giving a data of 15-meter resolution. So there is a huge cost whenever you want to purchase any images. At least for my study area, I spend around more than 1 lakh rupees for getting all the data. So like that, for smaller areas also, if you spending in a lakhs, that will be a cost bearing whenever do any GIS based analysis. And accessibility is also, as I said, accessibility of data. As we work in a government sector project also, there they have accessibility, like they can go to NRSC, then MRSAT. So for Maharashtra, there is a Maharashtra remote sensing center is there. So for that they will give the data to the government organization. But for when we use data for universities or private organization, they don't give accessibility to the map. They have to we have to write a letters and give get the access and something like that. So for this, they we say that they have a problem in accessibility. So, what will be the future trend of the remote sensing? As we all know that AI and ML will be the future trend for all the data. So, we use for downscaling of the data. We generally use random forest method and AI ML methods, because all the data you don't get for single same spatial resolution. So for AIML we use data to get more accurate and analysis, predictive modeling, real time monitoring also. And AI powered the system can support the water management and decision support system also. And also, as because we we also have a drone data, because we generally work for most of the areas, so we have drones. So real time monitoring with the help of drone and IoT based sensor will majorly help in the many project of water resource management, because